Swayam Prabha. Digital India. Educated India.
We continue our discussion on some basic concepts and the conservation equations. We will revise some of the basic concepts which are important for our ongoing discussion on governing equations, and till now we have been mainly talking about a general viscous flow model, but today we will specialize it for an inviscid compressible flow. We would like to discuss about thermodynamic pressure and mechanical pressure here. You may recall that in the last lecture we were talking about stress in a Newtonian fluid, and we said that there is a linear relation between the stress and the strain rate. You may recall that we had assigned an index n, and when that index n has a value of 1, then we have a linear connection between the stress and the strain rate. So, we are basically revisiting that equation once more, and you can see that when you look at that stress equation, there are contributions from the pressure, the shear stress, and the pressure, shear stress, and the bulk modulus, and you can write it using the index notation like we have over here, or you can write it like this in a vectorial form, where we have still retained the index notation as far as the Kronecker delta is concerned. And you may recall that when the indices of the Kronecker delta they match, that means I is equal to j, then it attains a value of 1, otherwise it becomes 0. Now, we would like to work out the expression for this sigma ij for the three different cases indicated here: sigma xx, sigma yy, and sigma zz, which are basically the normal stresses. And you may recall that in the stress tensor, these were the entries in the diagonal. Now, if you look at the original equation sigma ij over here, when I is equal to j is equal to 1, then you have a sigma 1 1, which is equivalent to sigma xx, and then the delta ij is 1, therefore, you get a minus p here. As far as the tau ij expression is concerned, you have to look at this equation. So, I equal to j equal to 1 would basically mean that you have a del u del x here in the first term. You would also have the same here in the second term, and therefore, you have 2 mu del u del x here. Then you again have Kronecker delta going to a value of 1 here times lambda times the divergence of the velocity. Therefore, this is the expression you get for sigma xx. When you apply the sigma ij equation where I equal to j is equal to 2, then you get sigma 2 2, which is equivalent to sigma yy, and then you only have a difference in terms of the velocity gradient here, because u 2 and u 2 here would mean a v, and x 2 over here would mean a y, and therefore, del v del y. That is how you get a sigma yy. Similarly, you get sigma zz. Here, of course, I is equal to j is equal to 3, and you have sigma 3 3 giving you sigma zz. So, these are all the normal stresses that we are talking about. Now, when we sum the three normal stresses sigma xs, sigma yy, and sigma zz, it gives us a tensor invariant. And the mechanical pressure is the negative 1/3 of this sum. Why negative? Because it is of compressive nature, and why 1/3? Because we are trying to average the effect. So, that is the average compressive stress on the element, and mechanical pressure is indicated with P bar. So, when you sum them up, you will see that it comes to minus 1/3 of, within the brackets, minus 3p 2 mu divergence of V plus 3 lambda divergence of V, which put together would give you this, where P is the thermodynamic pressure, P bar is the mechanical pressure. Thus, mean pressure in a deforming viscous fluid is not equal to the thermodynamic property which we call as pressure and indicated by P in this equation, since the term lambda plus 2/3 mu within brackets times the divergence of V is subtracted from the thermodynamic pressure to give you the mechanical pressure. Now, this would basically mean that if you were to take a difference between P and P mechanical, that is P minus P bar, what would you have? You would actually have this term, that is what we have mentioned over here, and we are calling this bracketed term as mu bulk because it is associated with the bulk modulus, and Stokes originally had put a hypothesis that lambda plus 2/3 mu would be equal to 0, which would mean that mu bulk is equal to 0 identically, but in later times it has not necessarily been found to be true for all kinds of media. From available studies, for example, for the gas nitrogen, in its molecular form we find that mu bulk is approximately 0.8 mu. For argon, though, it is 0. For methane, it is 1.33 mu, and so on, where mu of course is the molecular viscosity. Now, just trying to recall that the molecular viscosity, it resists the inertia of fluid particles during their motion, and mu bulk, it resists the compression during high applied pressure on the fluid element. So, this gives you an overview of thermodynamic pressure and how it is connected with mechanical pressure, and what role does the mu bulk play in between. Let us move on. We would like to address another few important basic concepts. One of them is angular velocity and vorticity. So, we have been talking about fluid flow for quite some time, looking at the basic issues, and we realize that when a fluid element is moving through a flow medium, the fluid element at time t, if it appears like this, as you follow it over time, it would translate, it would rotate, it would also deform. Now, if you consider a two-dimensional flow in the xy plane, for example, and we consider an infinitesimal fluid element moving in that flow field, at some point of time t, you may identify a fluid element of this form, which is rather nice in shape, something like a square or rectangular shape, and you are trying to follow it over time, and after a while you notice that it has taken up a shape like this. So, it appears that two adjacent sides AB and AC have rotated by some angle, and consequently the shape of the element has changed. It also has elongated a bit, and so on. So, as it translates along a streamline, it may also rotate, and in addition its shape may become distorted, as we have sketched in the figure. The amount of rotation and distortion depends on the velocity field. So, all that the fluid element is undergoing is by virtue of the velocity field which is advecting it. Now, the angular velocity of the fluid element, as we see in the xy plane, is the average of the angular velocities of the lines AB and AC. Let omega z denote this angular velocity. We can show that the omega z will be defined in terms of the time rate of change of those two angles theta 1 and theta 2, and from the geometry of the problem and the kinematics we can show that it is equal to half of dv dx minus du dy, typically we write them as derivatives, partial derivatives. Now, the omega z we have defined, and it so happens that when omega z is non-zero, we find that the curl of the velocity vector happens to be non-zero, and such flows are called as rotational flows. While if the curl of the velocity is 0, what we get out of it is an irrotational flow. When can rotational flows occur? Purely from the kinematics of the problem, you can argue that if those angles delta theta 1 and delta theta 2 are identical and they are in the same sense, for example, in the counterclockwise sense, instead of one being clockwise and the other being anticlockwise, we may end up having a solid body rotation of the fluid element, and then the omega basically takes up an expression like this. So, we will try to indicate that once more. So, the omega expression then takes up a value of this kind, and we therefore have a rotational flow. Now, delta theta 1 and delta theta 2 for a general situation may be unequal and non-zero. We are showing another possibility over here, where one of the deltas is 0, delta theta 2 is 0, while delta theta 1 is positive, and therefore, the element again will be displaying non-zero value of omega, and consequently, it is going to result in a rotational flow. Where can rotational flows occur? They occur in a lot of fluid dynamic situations, especially in viscous flows. We see them occurring in the boundary layer flows. That means flows near to solid boundaries where there is a strong velocity gradient. We see regions dominated by viscous flows like flow separation and so on, having rotational effects. In inviscid high speed flows where we have curved shocks, we can show that there would be rotational effects, there would be generation of non-zero values of omega and curl of v. In addition to the angular velocity effect or vorticity, we also talk about strain of a fluid element. So, when we have the delta theta 1 and delta theta 2 being non-zero, that means the fluid element has also got strained, deformed. So, how can we evaluate that extent of strain? In this case, the delta theta 2 minus delta theta 1 gives you the total angular deformation of the fluid element, and therefore, that would be the strain. And since it is happening at a certain time rate, therefore, it is basically a strain rate. In solid mechanics, we talk about proportionality between stress and strain, while in fluid mechanics, we talk about proportionality between stress and time rate of strain, which we were just mentioning in the previous slide. So, if you look at delta theta 2, it is del v del x into delta t. So, there is basically a time interval associated with it. If you look at delta theta 1, it is minus del u del y and again delta t, and though we are observing the event over a very short time interval where delta t tends to 0, you will always have a time rate involved. So, the time rate of strain, if I indicate it as epsilon x y, because I am looking at the element in the x y plane, then it is basically d theta 2 dt minus d theta 1 dt, and if you express that a derivative as a limit, then its limit delta t tends to 0, and then you have the ratios delta theta 2 by delta t minus delta theta 1 by delta t, which obviously comes out in a form like this here, where you can write it in the form of the velocity gradients del v del x plus del u del y, and we are showing some arrows over there just to indicate that the index that you have in the strain rate x y, the x and y figured here in terms of the independent variables, while the velocity components which arise in the numerator are corresponding to the coordinate directions which are in the other term. So, therefore, x maps with u here, y maps with v here. So, that is why we have indicated those arrows over there. From that logic, you can similarly define epsilon y z or epsilon z x, which will be in the y z plane, z x plane and so on, because we were talking about a 3-dimensional motion in general, and therefore, you would have strain rates occurring in different planes essentially, and therefore, it should be easy for you to define the expressions for the corresponding strain rates. When we do not have any net value of omega, so if you are talking about the xy plane, then it is omega z, and then omega z is equal to 0. That would also mean that the curl of the velocity is 0 in that plane, and that would result in a situation like this, that there is either a pure translation, no rotation of the element, or there is a straining of the element in such a manner, so that the delta theta 1 plus delta theta 2 gives you a value of 0. So, essentially the angles in terms of magnitude are identical, but they are in opposite sense. So, these situations create omega equal to 0, and therefore, you end up having an irrotational flow. When you have irrotational flow, then going by this vector identity that we have written, that is curl of a vector going to 0, and if you replace that vector, let us say the velocity vector, by gradient of a scalar, then it identically satisfies that vector identity. And in that case, we can say that in case of an irrotational flow, a velocity potential phi exists, which can express the velocity vector. So, the velocity vector can now be expressed as gradient of phi. So, this is the gradient operator operating on a scalar. Now, gradient of phi by definition is written in this form: del phi del x times I plus del phi del y times j plus del phi del z times k in the Cartesian coordinate systems, which of course is also equal to u I plus v j plus w k, which is the velocity vector by definition, and that would mean that u maps with del phi del x, v with del phi del y, w with del phi del z. So, we had a brief recapitulation of some of the basic concepts which are very, very important for us when we are discussing our governing equations, and here we have tried to put together all the forms that we have been discussing, and we are still talking about it in a very general sense, where we are accounting for the viscous effects, and therefore, you can say that this is basically Navier-Stokes equations written in all the possible forms that we have discussed. So, you may recall that we first of all defined a finite control volume. When we were sketching it, we took a volume like this, which was finite in size. We had defined small surface areas on that. We had defined elemental volumes inside that and so on. So, that was the concept of the finite control volume. And then we had the concept of a very, very small fluid element, the infinitesimal fluid element here, which is more like what we had drawn here inside the control volume. So, these were the two fluid models that we were talking about in terms of their extent, while another way of classifying them was that whether we are looking at the problem this way, that this particular control volume or fluid element is fixed in a laboratory frame of reference sense. If they are fixed, then it is basically an Eulerian framework, and then if you allow the control volume of the fluid element to move through the flow, that means get advected with the flow, then you are talking about a Lagrangian framework. That means both for a control volume you could have an Eulerian or a Lagrangian framework, as well as for a fluid element you can have a Eulerian or a Lagrangian framework, and you can move back and forth basically by using suitable rules of the game, as we say. Now, if I talk about the Eulerian framework, then we find that in the finite control volume, first of all, since we are integrating the fluxes, it may be mass, momentum or energy through the control volume surface, therefore, we see integrals. We can have surface integrals, we can have volume integrals, and all of them involve a closed surface basically. And if you look at the infinite signal fluid element, then you are talking about derivative expressions, because you are basically talking about conservation of properties at a point, because the fluid element is so small, it is almost like a point. If you move to the Lagrangian framework, on the other hand, the integral form remains for control volume, the differential form for the fluid element, but we see the existence of the d dt operator, the capital D dt operator, or the substantial derivative in place of the del del t that we were seeing in the earlier expressions. So, substantial derivative comes in order to bring in the Lagrangian sense, and therefore, there is a local time derivative plus there is an effect of advection that is taken into account. So, we should be recalling all these features in the different forms of the governing equations from time to time and revise them, so that they remain very firmly in our mind. We now talk about the Euler equation and the context of the Euler equation in the bigger framework, in the bigger picture. So, when we start talking about Euler equation from a general framework of Navier-Stokes equations, we say that we are just going to make only one change. There would be no viscous stress, and that is all. So, when you impose the condition tau I j equal to 0 in the sigma I j expression, then you remember there were originally 3 terms, now it boils down to 2 terms. One is due to pressure, the other is due to the bulk modulus. And then you can express Euler equations in 2 forms essentially. One is without body forces, the other is with body forces. In this slide, we are showing the one without body forces, and that is what we call as the compressible Euler equation. You are now quite familiar with the different terms that we have indicated earlier in the respective conservation equations. You may recall we had indicated them as A, B, C, D and so on. So, you may be finding them here. You remember that since sigma I j now has got simplified, you have fewer number of terms here. Moreover, you do not have the body force term here, which would otherwise have appeared on the right hand side. So, that is missing, and we have a few important notes at the bottom, which we had already discussed in the context of the thermodynamic and the mechanical pressure and the difference between the two, and how the mu bulk makes the difference between the two. And you should always keep it in mind that when you are talking about very strong shocks, there may be extremely high compressive effects. That is where it may make a significant difference. Now, in the next slide, we will look at the Euler equation with body force, which we often call as the compressible hydrodynamic Euler equation. So, here you see that the body force term has been added on the right hand side. Additionally, there is a q dot term which has been added in the energy equation. So, these compressible hydrodynamic Euler equations find a lot of use in astrophysical flows, which we will look at later on. You can incorporate MHD effects and so on. Now, we come to the conclusion. In this lecture, the following basic concepts were discussed. We talked about mechanical pressure and thermodynamics pressure and the role of the mu bulk. We talked about angular velocity and vorticity, strain rate, rotational and irrotational flows, how they are connected with angular velocity and vorticity, and the existence of a velocity potential in irrotational flows. We discussed about the governing equations of compressible flow in terms of the Navier-Stokes equations form for all the possibilities, the control volume, the infinitesimal fluid element, the Eulerian and Lagrangian approaches, and then we simplified now to the Euler equations, where we said that the viscous stresses are set to 0, and then we also looked at it with and without body force terms. So, all the possible forms were put together, and we have also looked at the inviscid form of the equations. Thank you.